Hello everyone. Today in this video we will study about several queuing models. First term means the stochastic distribution of the arrival time, and second parameter means the service time distribution, and third one means the number of machines or number of servers. And if this fourth variable is described, then this means the maximum number of customers allowed in the entire system. Okay, first model is the MG1. It means that single server from this one and with Poisson arrival distribution with unlimited capacity. Then you can see here the G is written here. It means that the service time follows the general distribution. In this example, we will the service time X follows the any general distribution with mean value and the variation. And number of servers is 1, and in order to be steady state, this utilization is the lambda over mu have to be smaller than 1. If this term is bigger than 1, then this model may explode to infinite. So with these variables, the several indexes from the utilization and the number of entities in entire model, and W means the time that entity have stayed in the model. And if Q denoted here, it means that this 2 is retained inside of the Q. So do you remember this figure? Then L and W means the entire number of entity and entire time that each entity stayed in the model. And LQ and WQ means the each time and number that is restricted to this Q area. And P0 means the probability of 0 entities in the model. If we assume that utilization is 80%, it means then 0.8, then this P0 is going to be 0.2 or 20%. It means that if the utilization of the server is 80%, that means there may be the 20% of whole simulation time would have 0 entities in the model. By use of these formulas, we are going to treat one simple example. Let's read. There are 2 workers competing for a job. 2 workers' name is Abel and Baker. Abel claims an average service time that is faster than Baker's, but Baker claims to be more consistent, even if not as fast as Abel. The arrival occur according to a Poisson process at the rate of 2 person per hour, or 1 over 30 person per minute. Abel's service statistics are an average service time of 24 minutes with a standard deviation of 20 minutes. While Baker's service statistics are an average service time of 25, that is longer than the Abel's, but a standard deviation is only 2 minutes. It's very, very smaller than the Abel's standard deviation. If the average length of the queue, it is LQ, is the criterion for hiring, which worker should be hired? Let's calculate. The arrival rate of the process follows Poisson process, and there is 2 customers per hour. So we can denote like this. And inter-arrival rate may follow exponential distribution because it is Poisson process. So in this case, inter-arrival rate will be 1 over lambda. Then is going to be 30 minutes per customer. So 1 customer arrives every 30 minutes in average. Then service rate of Abel and Baker. Let's calculate how it is going to be. With respect to Abel, the Abel service time, average service time is 24 minutes. So 1 over lambda. Lambda is a rate. So 1 over lambda is 24 minutes per customer. And standard deviation is going to be 400 minutes square. And utilization is lambda over mu. So Abel's utilization is about 80%. And if we apply this formula requires utilization and mu. 2 terms are required. So Abel's, if the Abel are working at this shop, then length of Q, LQ, may be calculated as shown in this example, and finally it is going to be 2.7 roughly. Now let's keep this value in mind and let's calculate the same parameters of Baker. Then 1 over mu is going to be 25 minutes per customer, and the square of standard deviation is 4 minutes square, and utilization is about 5 over 6. It's roughly 83%. Then length of Q is going to be 2.097 customers. So what is the result? In case of if the hiring criteria is selected based on this LQ, then Abel's LQ was 2.711. it means that if baker are working, then less customers are waiting, comparing with the case of Abels are working. However, the proportion of arrival who would find able find idle and thus experience no delay is P0 is going to be 20%, but the proportion of bakers is about 16.7%. So maybe the result can be changed based on what kinds of index is considered for the hiring condition. Anyway, in this case, with the LQ, baker wins. So it means that the smaller variability of service time secure the less waiting, the number of waiting persons, even though a little bit longer average service time. Now let's skip to second model. It is MM1. It is very simplest and very basic queuing model. Single server and with Poisson arrivals and very surely unlimited capacity. Actually, unlimited capacity have to be denoted here, the infinite symbol. Then, with respect to the service time follows exponential distribution. So, the mean service time is going to be 1 over mu. And also, the variance is 1 over mu square. And number of servers is 1. And in order to be steady state, the lambda have to be smaller than mu. And if this condition is satisfied, each calculation index is shown at this table. Okay, by use of this formula, let's resolve this problem. For the MM1Q with service rate of 10 customers per hour, now consider how the length of entire model and the entire staying time in the model increase as the arrival rate lambda increase from 5 to 8.64. It means by increments of 20% from 5, 6, 7.2 and 8.64, and then finally goes to 10. Then we can use these two formulas. Rho is lambda over mu, so mu is 10, so we can calculate utilization with respect to each lambda from 5 to 10. Let's check this number. It means that 100% utilization, and as you can remember, this is not allowed in normal queuing model with steady state. And lambda and W can be calculated like this with these two formulas. you can see this table. As lambda grows from 5 to 10, the rho reaches near 1, which is the boundary of statistical equilibrium. It means that in order to be the steady state, means that not to be exploded. This result growth of average customer in the system means that L increase according to the increase of lambda from 1.5 to 6.35 when lambda is 80 point, etc. And if the lambda is 10, then length of all the customers in the system is going to infinite number. Also, the average time that each customer are staying in the model is also going to the infinite. So in this case, if the lambda equal mu, it means that the service rate and arrival rate are same, that the model exploded. It means that this Q is increased and it's not stopped. It increased up to the infinite, and this server cannot have idle time. It's always 100% utilization. So this model cannot be sustained with the steady state condition. Now let's see the effect of utilization and service variability. This formula is the definition of variability. Actually, CV means that the coefficient of variation, and CV is defined as the service time and the deviation. So if we take a square here, then it is going to be going to this. Actually, we will not go into detail of this variability calculation, but you have to remember several the insight from this variability. First one is that in case of exponential distribution, in the case this coefficient of variation is equal with the 1. It is very important characteristics of variability. So if this CV equal to 1, then we can use this M here. Reversely, if the M is written in Kendall rotation, it means that the arrival rate and the service rate follows the exponential distribution, and the relevant coefficient of variation is 1. Now, how it impacts on the length of the queue. We have already seen this LQ here, this formula. let's keep this formula to here. And this formula can be rearranged into this term. And the first term is very equal with the LQ of MM1, this term. It is equal. And the second term only have this coefficient of variation. So this is the correlation factor that corrects the MM1 formula to account for non-exponential service time distribution. Means here, non-exponential means the general distribution. So this is the only correction factor. It means that this is not the analytic solution. So if CV is near 1, then this LQ is very accurate. However, CV is very larger than 1 or very smaller than 1. In this case, this approximation cannot be used for the actual calculation of queuing model. So in that case, we have to compare with the dynamic discrete event simulation. Those works will be conducted in later lectures, and each queuing models will be compared with the discrete event simulation. So please remember this, the CV, coefficient of variation, and also this approximation of LQ term. Now let's see the multi-server queuing model. And here you can see this number. It's not 1 now. It is changed to a certain number of C with the infinite number of customers. Those are allowed in the system, and this means the size of calling population. Actually, those two parameters can be omitted. If these two variables are omitted, it means that both parameters are infinite. Anyway, service time follows the exponential distribution because M is denoted here. And number of servers, this is C. Let's number of servers be N. And steady state. To be steady state, the utilization have to be smaller than 1. And one change occurred here. This is C. This is very the intuitive, because let's think the two persons per hour arrived, and this is mu. 3 persons or 3 entities are treated in server, and this is lambda, and this is mu. If the number of C equal 1, then utilization is 2/3, is roughly 60-70%. But if this machine is increased to 2 machines, then in this case these arrival entities are divided into 2 servers. So this roughly 67% are divided into both servers. So in this case, row utilization row is divided the number of servers. It's roughly 33%. So in case of multi-server queuing model, utilization is written as like this. Here it is same thing. And the calculation of the probability of 0 customers and probability of that number of customers are larger than C, and length and staying time are calculated like this. It is very, very complex. So if any of you really want to prove this kinds of calculation, then please let me know. I will let you know the reference material about queuing theory. But in our lecture, I don't want to prove each of these formula. Instead, just I want you to remember what kinds of queuing models are there, and how those related the indexes are calculated. So now let's go to this example. Let's read the example. I will give you 30 seconds. Okay. Many early examples of queuing theory applied to practical problems concerning tool creeps. Attendants manage the tool creeps as mechanics assumed to be from an infinite calling population. It means that there are no limitation of the resource, or it means that the server can have the resource that are required at any time. However, this example could as easily be customers arriving to the ticket counter at a movie theater. Now assume Poisson arrivals at the rate of 2 mechanics per minute and exponentially distributed service time with mean 40 seconds. Now let's calculate with the assumption of just one server. So arrival rate lambda is 2 mechanics or 2 customers per minute, and service rate is this lambda over mu is becoming like this. It is larger than 1. No, not this one. Just calculation of the service rate. From here, the service time follows the 40 seconds average time with the exponential distribution. So we have to convert it to minutes. So service rate is 1.5 per minute. So we take both parameters to the calculation of utilization here. Then utilization become larger than 1. It means that if we stay here, then this ticket counter, so queue, the waiting area will explode to infinite as time goes on. If it's going to be practical case, this means that more servers are needed to satisfy the statistical equilibrium. So in this case, the lambda over mu is 4 over 3, and the number of servers have to be bigger than this as an integer number. So in this case, required number of server is at least 2. It can be 3, 4, or 5, but the smallest number is 2. Let's assume that there are 2 servers, and this is the calculation of these queuing models. In this case, with the 2 servers, the probability of 0 customers is 20%, and the probability of the customer over than the 2 persons is about 50%. And the LQ and L, also W and WQ, can be calculated as like this. If 2 servers exist, then the length of average number of lengths of queue is about 1, and the entire model can have the 2.4 mechanics in average. Also, the average waiting time in the queue is about 0.5 minutes. It's roughly 30 seconds. So this is a very good example for the design of any kinds of the service system. And this is again the explanation about the variability. Actually, we have seen the, where is it? Here, MG1. This term can be divided into these 2 terms, and the first term is coming from the LQ of MM1 model, and second term is the correlation factor for the approximation from the MM1 model to MG1 model. As you can remember, in actual theory, the indexes are not calculated from the basics. Instead, the indexes of this model is calculated by approximation with the use of the variability term, and it is the aligned with the MM1 model. So it's in this page also explains the same mechanism. It means that this queuing model MGC, the indexes of this queuing model can be approximated by use of MMC model. Then correlation factor is the variability term that is already explained in coefficient of variability. And very surely, the nearer CV is going to 1, then the result is better. It gave us the better approximation. So those terms here or here can be deduced from, where is it? MGC, MMC, from this table. So just remember what kinds of solution, where is the each solution of the queuing models. Now let's see about the MG and infinite model. It is far simpler than comparing with the previous examples because the infinite number of queue means that self-service system. It means that there no needs for the assigning the finite number of servers. Service capacity very far exceeds the demand. Then this model can be used when you want to know how many servers are required so that customers will rarely be delayed. It means rarely be delayed means that no delay. It means the customer do not delay at any time. And this formula explains this model. And now how it is worked in real case. This is the example for the use of this formula. And actually here is infinite capacity of model, but by use of this we can determine the appropriate number that is needed for the given number of the arrival rate and service rate. I'll give you 30 seconds for read this problem. Okay, now let's read together. Prior to introducing their new subscriber-only online computer information service, or you can replace this word to the online computer game. The connection must plan their system capacity in terms of the number of users that can be logged on simultaneously. Can be logged means that can be stayed in the server during the running the information service or very possibly in case of the online computer game. If the service is successful, customers are expected to log on at a rate of 5% per hour. This is arrival rate, according to Poisson process, and stay connected for an average of the 180 minutes, roughly 3 hours. In the real system, there will be an upper limit on simultaneous users. It can be explained in Korean, 동시 접속자 수. But for planning purposes, the connection can pretend that the number of simultaneous users is infinite. This is first assumption. And to ensure providing adequate capacity, this might be the service rate or service satisfaction ratio. 95% capacity of the time. How many simultaneous users the connection should allow? Actually, connection, the reason why the first character is capital is that maybe connection, maybe the number of the online company. So the solution is really the simple. Only one formula is used here. Now, do you remember what this means? This means the probability that the number of customers are stayed in entire model. So in this example, the design variable is the 95% capacity. It means that 5% are the safety factor. So in order to be 95% the design variable, the where is it? This is number of the customers. So by use of the here, this is the probability of n, and this is the 0.5, and we need 3 parameters here. This is the function of lambda, mu, and number of persons or number of servers in the system. So we have already enough information about lambda and this mu here, and from here this implies that expected number of simultaneous users can be calculated with this formula. Is roughly the 100 or 1,500 simultaneous users, and with this we can use this formula here, and from this, in order to secure 95% the capacity of this system have to be about the 1,564 the simultaneous users satisfy this requirement. So some of you who like the online game, computer games, the online computer game company may calculate this kinds of calculation when they launch new game, and before the open the online service, they may have to calculate the simultaneous user number, and also according to these expected simultaneous user numbers, the appropriate number of servers have to be equipped. So this is very good example for that the queuing models are used in our real life. This is the last one. Here is multi-server queues with Poisson arrival and limited capacity. Limited capacity are denoted here. The fourth parameter means the maximum number of customers allowed in the system. Actually, we call it this blocked number. It means that even though there are the exceed number of customers that is waiting at the calling population, but if the number of entities in the model already approach this number, in this case, any entity cannot transferred to this queuing system. So there exists a limited number of customers in the system. The steady state inequation, the utilization is smaller than 1, is not needed anymore. Instead, for any value of lambda and mu, except only utilization is 1, the statistical equilibrium can be satisfied. Here, when you are interested in what will be happen when utilization is 1, you can find these theoretic papers in Google Scholar. Okay, and relevant indexes can be calculated with these given formulas. Maybe in our actual simulation study, this model might be frequently referenced in order to compare with discrete event simulation model, because I let you keep any kinds of limitation of the entire number to be finite. So please remember this case. This case means that the multi-server and also with the condition of limited capacity.